and welcome to this week's annual seminar. And today we are very glad to have Arindam from Alabama, and he's graduating this year and applying for postdoc positions. And so today he's going to talk about searching for heavy neutrinos at the LHC. So let's welcome him.
Today I'm going to talk about the heavy neutrino phenomenology at the LHC. So in the abstract you might see that it is at the colliders, because initially I thought I would include the ILC stuff, but I got rid of the ILC stuff. So it is just on LHC. So we have the very well-known standard model with the lepton doublet, right-handed electron, and the Higgs doublet. And recently these neutrino oscillation experiments proved that these flavor eigenstates of the neutrinos can be mixed with each other, and which can invoke the idea of neutrino mass in the standard model. But in standard model, the neutrinos are all massless. In 1979, Weinberg gave the idea of a dimension 5 operator in standard model, and basically this idea was the father of some new mechanism which included some right-handed heavy neutrinos to extend the standard model, and eventually explained the small neutrino mass where we have one Majorana mass term. The mass matrix, if we diagonalize this mass matrix, we can get the light neutrino mass term. We can get the light neutrino mass term, and if this heavy neutrino is of the order of like some 100 GeV or in the less than TeV scale, then we can produce this heavy neutrino as at LHC through the neutral current and charge current interactions. Okay. Apart from the seesaw mechanism, initially what I told, that we can have one more possibility of extending the standard model, and we can do it using two Majorana heavy neutrinos, and we can have a small lepton number violating term which can generate the light neutrino mass from this mass matrix. So here is the lepton number violating term, and if we consider that our mixing is of the order 1, then the neutrino mass is proportional to the light lepton number violating parameter. So other way, if the lepton number violating parameter is very small, then we can fix our mixing angle of the order of 1. But if we consider the phenomenological constraints from the lepton flavor violation, we will find that this assumption of taking the mixing angle of the order of 1 is not fully correct. So using the phenomenological constraints, we might see that this mixing angle is much less than 1. So this heavy neutrino can be mixed with the light neutrinos through its flavor and mass eigenstates, and it interacts with the W and Z boson through the charge current and neutral current interactions. Because we have the mass flavor eigenstate here, and we have written this flavor eigenstate in terms of the mass eigenstates. So once we write this charge current and neutral currents in terms of the mass eigenstates, then we get the mixing and the interaction between the heavy neutrino and the lepton through the W boson, and the heavy neutrino and the standard model neutrino through the neutral current interaction. Okay, previously I told that we have some phenomenological constraints, and the biggest constraint comes from the mu to E gamma process, and this is the mu to E gamma process paper, and the current analysis is given here, and that is of the order of 10 to the power minus 5. And this process constrain our analysis, rather the mixing, very high, so that it cannot be order 1, and eventually it becomes much less than 1. So using these constraints, we try to fix our mixing parameter, and to do that, we consider two hierarchies. One is the normal hierarchy, and another is the inverted hierarchy, and we use this neutrino oscillation data to fix our model parameter, the mixing parameter N and R. Okay. So what we do, that we assume that our heavy neutrino is a degenerate one, and we can write this this light neutrino mass in terms of the UMNS matrix, and these are the diagonal matrices, and we have given the form here, DNH and DIH. So for this analysis, what we do, we use two kinds of flavor structures. In one flavor structure, we consider that this mu is proportional to the unit matrix, and MD is the Dirac mass matrix, which is non-diagonal. And the other structure is, we consider MD is diagonal, where mu carries all the flavors. And now one can write down the MD in terms of the UMNS, because MD is actually R, this R is actually MD over M. Then one can express MD in terms of this UMNS matrix and the square root of this D, NH and IH. So the square root of D, NH and IH is this type of matrix we have, and for the flavor non-diagonal case, we have MD over M, the mixing, following this structure. And the flavor diagonal case, we can make this M mu is MD square M times mu, and this mu is proportional to the unit matrix. So our N dagger is a non-unitarity matrix, and it has been shifted from the diagonal 1, and here this 1-2 component is a severely constrained parameter from mu to E gamma. And we can calculate our flavor diagonal and flavor non-diagonal cases for this mu using these matrix elements. And we can find that this mu term, which is proportional to the light neutrino mass, is of the order of some electron volt. So therefore, the interesting thing is, this mu term cannot be obtained in LHC. So that when we produce our heavy neutrino at LHC, then it can overcome this mu, this lepton number violating term, and readily produce the signal as the Dirac heavy neutrino. So therefore, we call our heavy neutrino as a pseudo Dirac one. It's not a Dirac one. It's a Majorana type heavy neutrino, but it shows the nature like a Dirac neutrino. So we do one more thing, because in the previous parameterization, the cross section we got was very low, especially in the flavor non-diagonal case. So what we do, we try to generalize our mixing matrix so that we can get some, we can gain some cross section from that. So to do that, we use an orthogonal matrix inside our mixing matrix, and we find that our mixing, if we calculate this R star R transpose, then this R star R transpose is a function of this y parameter, not on the x. So if we calculate this O star O, then it becomes a function of y, not on the x, because x and y are all general parameters. And similarly, this R and R star R transpose are the functions of the Dirac phase and the Majorana phase and the unknown y parameter. So what we do, we produce this particle at the LHC from Q cuboid prime interaction through the W plus, and then this heavy neutrino shows the trilepton signal. And here we have considered the texture like L plus, L minus, and L plus with a missing energy. And here the leptons are like either electron and muon, because we have considered two generations of the heavy neutrinos, and these are the two degenerate heavy neutrinos. And to perform the parameter scan, we consider the heavy neutrino mass at 100 GeV, and we consider the collider energy at 14 GeV, and we run the parameter scan on the Dirac Majorana phases from minus pi to pi, and the unknown parameter y, it is run from 0 to 1. First, we show you the cross section for the fixed parameter region. What we did in this slide. So, using these parameters, we got these cross sections like electron-electron inverted hierarchy, and then this is the mu-mu inverted hierarchy. This is the electron-electron normal hierarchy, and this is the mu-mu normal hierarchy. And this is the flavor diagonal case for electron-electron, or you can say that it's a dilepton. So we have seen that the number of events for the electron-electron and mu-mu cases at 30 femtobarn inverse with m equal to 100 GeV is much lower than the standard model backgrounds. Though the muon case is little better than the electron case, but the flavor non-diagonal cases are almost hopeless. But the flavor diagonal case has some comparable significance with the standard model backgrounds. So then we studied the general parameter set. Here I am showing you only the dependence only over y, and I am not giving the Dirac and Majorana phases here. But y is this unknown parameter, where we introduce this orthogonal matrix to the mixing. So we generalize this matrix with some x and y, and then if you write R star R transpose, that is the mixing square, then this mixing square is proportional, cross section is proportional to the mixing square. And the cross section is independent of x, it is just a function of y, right? So therefore,
so in your standard model background, why your EE is so much higher than mu mu? It's almost factor of 2 higher.
Actually, this background analysis was not done by us.
Okay.
It was done by a paper called De La Villa and Saavedra, and we just constrained our result according
to
which
backgrounds they considered.
Mostly in case of trilepton, you will have the irreducible background, right?
Okay, let's.
I'll show you. Because this analysis, this background analysis is not done by us. It is done by them. Which at that time we did not have the technology of doing the background analysis. So we just calculated our cross sections, and we calculated the efficiencies from their calculation. So they had some before cut and after cut events. So we calculated the efficiency from them and used that efficiency in our result. Therefore, we got our result after putting cut.
Yeah,
Okay.
WZ is one background.
WZ is one background, and of course misunderstanding.
Yeah, I mean,
WZ is a very important background and the misunderstanding. Because WZ will give you the irreducible background.
yeah.
So any kind of analysis like that, that irreducible background is a leading background.
Yeah.
And once we had that general scan with the inclusion of some unknown orthogonal metrics in the mixing parameter, we got such enhancement, which is written here. So these are all in terms of the cross sections. So if you have the electron at 0.5, so if you multiply this by 30, then it will be 15, of the order 15 or 16. So in our previous case, we have the number of events as 0.2, 0.3. And in case of mu, the number of events are 1.61. So in our case, after the enhancement, it will be of the order of 180. So we got this enhancement because of this unknown, because of the inclusion of some unknown parameter. So what we do after that, we pick up the flavor diagonal case because its cross section was very high, and picking up the flavor diagonal case, that is also called the flavor democratic. What we do, we used some CMS result to constrain our analysis and to put the first direct bound on the heavy neutrino, the pseudo-direct heavy neutrino mixing angle, rather the light heavy mixing angle at 8 eV. So to do that, we have two benchmark scenarios. One is called the single flavor, and the other one is called the flavor diagonal case. In case of single flavor, the heavy neutrino is coupled with one lepton, say electron or mu. And in flavor diagonal case, there are two generations of heavy neutrinos, and one heavy neutrino is coupling with one electron, and another heavy neutrino is coupling with the mu. And once we do it, we study the trilepton signal. So from this one, we have studied the Q-cubed prime production and the quad-gluon fusion. So once we have studied the quad-gluon fusion and quad-gluon fusion, then this quad-gluon fusion gave some enhancement on the Q-cubed prime. So if you have Q-cubed prime alone, then the cross section is much lower than the Q-cubed prime plus QG. So we produced the heavy neutrino with the lepton, that is Q-cubed prime mediated by W, and W gives the lepton and the heavy neutrino. And from the QG, we have this W, and W produces the lepton and heavy neutrino. So we plot the cross section as a function of mass, and we see we use a PT cut around 30 GeV because this PT cut is used by the CMS paper, which we used for constraining our analysis. And we noticed that the 14 TeV one-jet process is this 14 TeV one-jet process is very close to the 14 TeV zero-jet process. And this one-jet process dominates. So yes, this one-jet process is 14 TeV one-jet process is very close to the zero-jet process at 14 TeV. Yes. So this analysis is done by me, and my collaborators in this paper. So after we get the trilepton and missing energy event, we use the CMS search for some anomalous multilepton process, where they studied the trilepton and the 4-lepton processes separately with some missing energy. So as they have the trilepton search, so we can easily adopt that search in our case, or to constrain our analysis using their search. So what we do, we used these PT lepton cards and PT jet cards, eta cards and separation cards, and we consider this missing ET is less than 50 GeV. We consider two regions according to the CMS analysis. One is less than 75, that is below the Z-pole, and another is above the Z-pole, that is MLL opposite side, same OSSF, that is the same sign, opposite sign, same flavor, above the Z-pole. And in conservative analysis, we have got that when the invariant mass is below the Z-pole, it is 37 events excess, and above the Z-pole, we have 13 events excess. And these analyses are all done at the 95% confidence level. So we have the degenerate heavy neutrinos. So once we have the single flavor production, to get the flavor diagonal production, we can just gobble it, because the heavy neutrinos are all degenerate. So doing that, we can get the bound on the upper bound on the mixing for the single flavor case and the flavor diagonal case. And to do that, we compare our results with L3 and the electroweak precision data. The electroweak precision data is parallel to the horizontal because it is independent of the heavy neutrino mass. So this is the ATLAS result at 7 TeV, and these are the projected 14 TeV search reach, what we have calculated just using the 8 TeV data. We just scaled the 8 TeV data to the 14 TeV. And our flavor diagonal case at 8 TeV is comparable with the Higgs data. It is just a factor of some factor different because it is a log scale, therefore it shows a little bit lower than this one. And our at 91.2 GeV heavy neutrino mass, this result is comparable to the electroweak data. This is for the mu, and this is for the electron.
So precision data means oblique parameters, or what precision data you are using?
The lab data.
Okay.
So now we want to improve our given bounds, including all the possible heavy neutrino production channels. And this paper has recently come out in arXiv. And in that case, we have included the zero jet process, which is Q bar prime, and the one jet processes came from the quad gluon fusions, and we have also introduced the two jet processes from the quad two jet, quad gluon two jet, and the gluon two jet processes. We have also introduced this photon mediated processes. The analysis of the photon mediated processes are done by P.S. Gopaldev and his company, and Daniel Albert Awan and Richard Rillis last year. This has been published this year. It came in arXiv last November. So in this photon mediated processes, they analyzed three types of processes. One is called the proton-photon interaction. It is also called the elastic and inelastic. In the what is called the elastic process? The elastic process is something like that the proton is going and it radiates a photon, and then that photon interacts with another proton. And there is another process called the inelastic process, where the initial proton fragments, and then the parton radiates the photon, and then that photon interacts with the remaining proton. And another is the final one is the proton-proton QED process. Is the two-jet process. This is called the inelastic process according to them, because all these protons are fragmented, and then they have the W gamma interaction to produce this two-jet process. So we have considered all these processes to improve the upper bound on the mixing angle, and we produced our heavy neutrino with the associated lepton. And in this case, what we have noticed that this is the one-jet process. This one-jet process dominates over the zero-jet process when the PT jet cut is 10 GeV. So for one-jet and two-jet processes, we used 3 different PT jet cuts to keep our analysis collinear safe. So we have like 10 GeV, 20 GeV, and 30 GeV jet cuts. Later we will use only the 20 GeV jet cut and the 30 GeV jet cut, because 10 GeV jet cut is not high enough to deal with. And the CMS and Atlas are also using the 20 GeV and 30 GeV jet cuts. So if we want to compare our results, we need to do that. So the left panel shows the 8 TeV result, and the right panel shows the 14 TeV result. And for 30 GeV one-jet, it is completely dominated by the zero-jet particle line. The same thing happens at the 14 TeV. And this is the two-jet process. We use the same jet cuts in two-jet process. This is the 8 TeV and this is the 14 TeV. And we notice that in 14 TeV, this 30 GeV jet cut dominates over this QQ zero-jet process at very high heavy neutrino mass, like around 800 GeV. But 800 GeV, then the heavy neutrino will decay and it will have some mixing. Then the production cross section will not be that much impressive at 800 GeV heavy neutrino mass. So we can restrict ourselves around like 500 GeV heavy neutrino mass. So now we pick up our one-jet process, and in one-jet process we have the quark-quark one-jet and the quark-gluon one-jet. And now we plot our quark-quark one-jet and quark-gluon one-jet separately. So once we plot this quark-quark one-jet and quark-gluon one-jet, we see that the quark-quark counterpart always dominates over the quark-gluon counterpart. We suspect that it is because the Bjorken scaling parameter, where if we go to the high Bjorken scaling parameter, then the quark PDF is greater than the gluon PDF, right? So that could be the reason why the quark-quark one-jet dominates over the quark-gluon one-jet process. And if we go to the lower mass region, like say 80 GeV or so, then there is a possibility that this quark-gluon one-jet could take over the quark-quark one-jet process, because one parton will have a low Bjorken scaling and another will have a high Bjorken scaling. So it will be possible to produce one low mass particle at the LHC using that combination. We do the same for the two-jet processes. We separate out the QQ bar prime, the QG, and the GG initial states. For the QQ and QG, we find the same situation what we got in the one-jet case. But the two-jet case, the gluon 2-jet case is always dominated by this QQ 2-jet and the QG 2-jet. So we suspect that the two gluons have not the Bjorken scaling simultaneously small to produce the heavy neutrino at the LHC. Right? We also plot the photon-mediated processes. We separate out these elastic, inelastic, and deep inelastic processes. And separating out them, we find that the deep inelastic, elastic, and the inelastic processes dominate over the QQ 0-jet process after a certain higher heavy neutrino mass, say around 600 or so. But all these photon-mediated processes are much lower than the quark-initiated process like QQ bar prime, QG, and the GG processes. So considering these processes alone will not be a good idea to produce the heavy neutrino. So if we add these photon-mediated processes, we get a very little enhancement in the production cross-section. Okay. Recently, Atlas and CMS has performed the same sign dielectron production. The same sign dielectron production means they have the type 1 seesaw. So standard model is extended by one right-handed Mariner neutrino, and that right-handed Mariner neutrino will produce the same sign dielectron. N will decay into N will be produced with some L plus, and then N will decay into another L plus and W will give two jets. So once they did this analysis, they have this cross section as a function of mass this is by Atlas at 20.3 femtoward inverse, and this is by the CMS. They did the analysis from like 40 GeV heavy neutrino mass to 500 GeV heavy neutrino mass, and both of them have the analysis at the 95% confidence level, and these are the published papers. And they did at 19.7 femtoward inverse luminosity. And both of them considered PT jet greater than 20 GeV. So using all our production processes, we plot the mixing angles for the type 1 seesaw at 8 TeV and at 14 TeV. 14 TeV is the projected search reach. At 8 TeV, we have considered the mass from 100 GeV to 500 GeV, the same thing done by Atlas. And we have noticed if we pick up the 100 GeV heavy neutrino mass, then the Atlas mixing angle is given 0.0035, and our 0 jet is also comparable to the Atlas result. So we have added the 1 jet processes, and we have improved our mixing angle a little bit, and then we have further improved our mixing angle using the 2 jet processes. And we have compared our results with the existing limits. And this is the projected search reach for the 14 TeV. This is at these lines are at 300 femtoward inverse, and these lines are at 1000 femtoward inverse luminosities. Now we pick up the CMS result, and using the CMS same sign dielectron, we do the same. We compare our result with the given CMS and Atlas results, and we find that at heavy neutrino mass 100 GeV, this is the CMS prediction, and our 0 jet mixing angle square is 0.005086, and we can improve these mixing angles using 1-jet and 2-jet processes, quite a high order. And this is the 14 TeV search reach for the same sign dialectal using the CMS data. Okay. And now we improve our trilepton result. So we have included this 1-jet and 2-jet processes for the trilepton analysis, and this is the single flavor case at above Z pole, and this is a flavor diagonal case at above Z pole. These are the initial results, and these are the final results after including the 2-jet and 1-jet processes. So here are the results for the below Z pole. So we have given a projected search reach for the 14 TeV data. So this is the electric precision data for mu, and this is the electric precision data for electron. So now we can conclude our presentation that we have done some general parameter scan to enhance the cross section of the heavy neutrino production. We have done some we have calculated the direct upper bound on the mixing angle square using the trilepton plus missing energy, where we have used some given result by CMS for the luminance multi-electron search, and we have studied the initial states such as quark-quark-quark-gluon and gluon-gluon, and we have separated the production channels from these processes, and we have given the upper bounds on the same sign dielectron plus dijet using the type 1 CISA, and we have improved those upper bounds giving including the 1-jet and 2-jet processes. For the inverse CISA, we have done the same. We have first given the analysis for the 1-jet process, and then we have improved our analysis using the 2-jet processes, and we give a prospective search reach for search reach at the 14 TeV ellipse. Thank you very much.
Any question for Arindam?
So for different
the backgrounds, okay. Your backgrounds are here.
Okay. So QG, all these processes, did you take it from MATLAB or did you do the theoretical?
MATLAB.
But
I think in the next paper I will do this.
But when you take these channels separately, are they gauge invariant?
Of course, always. Because you don't need to take these processes separately. You can generate these processes separately also in MATLAB.
Yeah, I mean you can do that.
Why are you asking that they are not? They may not be gauge invariant? Why do you think that?
Yeah, I mean sometimes if you just pick one channel, I mean MATLAB, the way MATLAB calculate the interference between different channels, so you have to be careful about that.
Okay. That
those numbers may not be.
We have checked our calculations using using our mathematical analysis. So
yeah, because the way they take into account interference.
I know. Some unitary evaluation may occur.
To show that this dependence on your mixing parameter y, so do you have plots for this the other angles? See this CT and the Majorana angles. Do they have any distinguished powering by?
Not that much importance in the Dirac or Arindam phases. Those are almost same. Like that may not be that much interesting. Therefore, I did not include it.
Because I thought having those angles, that probably doesn't really change the magnitude of the coupling.
Yes.
So unless you have interferences, otherwise you probably don't see them. So they do look like they are almost
same.
Oh, okay.
Yeah. Therefore, I did not put those things.
Yeah, because the CT angle, you can measure from the oscillation. Majorana angle, you cannot. If there's any other place you can measure the angles.
Yeah. That's right. I put those plots in my paper, but talk.
I see. So it looks like those cross sections, you still have some hope of maybe at
Yeah, we did not do that flavored non-diagonal. That is F and D analysis, but yeah, we talked previously. Yeah. If we can do, then there may be some hope, because this mu channel is kind of this is the trilepton channel after the heavy neutrino decay. So 6 pentagon. So we may have some hope in some higher luminosity.
any other questions? Well, we still have plenty of time. So if you have any questions or want to have some discussion about heavy neutrinos, you're welcome to discuss it with our speaker. And if there are no more questions, I think we can let's thank Arindam again.
This is the thing you got checked, but I don't know if this is what you wanted, but no, there's still more files. But
Do you agree with the numbers?
Yeah, I was
Afraid that was the answer? Yeah.
I can't imagine a situation where even an activated source would be even comparable to a.
And we're so close to the thing already.
That's
I mean,
right, yeah.
If we were comparing tabletop to 30, 50 meters.
PA.
If it did work, it would be
That's the one I
It would be astonishing.
I thought it was out of 200 plastic on my course.
Yeah.
So you are actually thinking maybe some fighter with a laser beam.
Okay.
But
This photon is not the laser. It is the photon coming from. This is a proton. This is a proton. The proton radiates the photon,
Yeah.
and then some some you after the fragmentation.
It's a
You get.
Hmm? It's the problem of